Okay, so part 2 of this lecture, I'm going to talk about quotient groups. And the way to think about these is we're going to try to do what we did with modular arithmetic at the very beginning of this term, right? We started off with a nice algebraic system, the set of integers, and we put in some new rules and try to figure out what we got out of that. So for integers, we said that Z mod NZ, which is a group, we didn't know it at the time, but it's a group. Z mod NZ is the group of residues mod n. And the new rule is that A will be congruent to B modulo n whenever n divides B minus A. So we haven't seen our division symbol in a while. It's good to see them back. So the whole point of this exercise was we got new tools for understanding the integers themselves. By grouping down into these residues, we learned new things about what distinguishes prime numbers from composite numbers. And more to our purposes in developing cryptography, it was inside the group of residues that we defined our RSA encryption and our Diffie-Hellman key exchange. All of those were done using modular arithmetic. So if we want to try a similar thing with other groups, what do we need, right? So yesterday, I introduced subgroups. I said that the set n times z will be the set which is all the multiples of n, and that is in fact a subgroup of z. So my hint from yesterday is if we know that this is a subgroup now, and this notation, z mod nz, is the notation that we've been using for residues mod n, what does this have to do with groups in general and subgroups in general? So how do we get this to work for other groups? So this is the definition. It's a bit restricted. I'm going to work under the assumption that G is an abelian group just to avoid some technical details. This can also work for non-abelian groups, but you need additional conditions on H, and I don't want to deal with that right now. So the setup is G is an abelian group, H is a subgroup of G, and I'm going to define a new group, which I call the quotient group, G mod H. So you can think of this, on my previous slide, this was group of integers modulo the group which is multiples of n. Since I'm working in the abstract, I am going to use star, just a generic star, as my operation. Maybe this is addition, maybe this is multiplication, maybe this is function composition, or doing one symmetry and then doing another symmetry together. It can be any operation you want. I'll say that elements A and B in the quotient group, G mod H, are going to be considered the same as long as A combined with the inverse element of B is an element of H. So again, I find it very helpful to think of this in terms of modular arithmetic. So if I was looking at integers mod 11, my group G is the set of integers. My subgroup H is the group which is all multiples of 11. How do I know that two integers are the same mod 11? My operation is plus, right? My operation is addition in the integers. My inverse elements, I've written it here with an exponent, but really that should be negation, right? The inverse of 2 under addition is negative 2. So how do I know that 13 and 2 are the same mod 11? That's because 13 plus -2 is 11, and 11 is one of the elements of the multiples of 11 group. This is what that relation looks like in general. So I don't know what the operation star is. That will determine what inverting looks like. So maybe this is reciprocals, maybe this is negation, maybe this is inverse functions. Just whatever inverse corresponds to this operation star. How do I know that two elements are the same? It's because combining the one of them with the inverse of the other lands me in the group which I am modding out by. So I could say this is G mod H. I've modded out by H. Let's explore another example. So what group could be more familiar than just the real numbers? If I take the set of all real numbers, my group operation is going to be addition. Good old just adding real numbers together gets me another real number. And adding in the real numbers, it doesn't matter what order we do things in, so I've satisfied my condition that the group is abelian. I need to have a subgroup here, right? So according to yesterday's lecture, I want a set of real numbers which is still a group under addition. So I'm going to pick the multiples of 360. So every integer multiple of 360, that is still a real number. So this set of all the multiples of 360 is a subset of the real numbers. And is it a group? Yes. 0 is equal to 0 times 360, so it has an identity. I know that the negative of one of these integers is still an integer multiple of 360, and that's good. And I know that if I take the sum of any two of them, then that will still be an integer multiple of 360. So yes, this is a subgroup of the abelian group R. So my quotient group is going to be R mod 360Z. It's kind of a funny name for a group. What is the new rule that I have? Two real numbers, A and B, are going to be considered the same in my quotient group so long as B minus A is some integer multiple of 360. So B minus A has got to be equal to 360 times n for some n in Z. So again, this is very familiar to the way we defined modular arithmetic, right? This almost looks like the integers mod 360, except that this would be Z here as the containing group. We've been modding out by the subgroup 360Z, but we didn't originally define that in terms of groups. We just said that we're wrapping around at 360. We're effectively doing the same thing here, wrapping around at 360, but using the entire real number line instead of just the integers. So maybe pause the video and try to think of what group that we have already seen that this describes. Aha, here we are. So this group where we're taking the real number line and wrapping around at 360 is functionally identical to the circle group I had a couple lectures back, right? So in my circle group, I said that my group elements are radian measures from 0 to 2 pi, wrapping around so that 2 pi radians is equal to 0 radians. And then in that system, adding those angle measures worked exactly like we've seen from geometry. I claim that the quotient group that I've just defined real numbers modulo integer multiples of 360, that's also the circle group, just using degrees instead of radians. So I can think of my group elements as being degree measures. The smallest one that I want is 0 degrees. And the largest one, I'm going to say 360 degrees, wraps back around to be 0 degrees. And in some circumstances, you might want to talk about negative 10 degrees, just as a handy thing to talk about. But negative 10 degrees really is the same thing as 350 degrees because of the way that we are modding out by that subgroup. So I would say that 350 degrees minus negative 10 degrees gets me 360 degrees, which is the 0 element. So those are going to be the same in my quotient group. So this is another tool that we can use to try to boil down a group, a very large group like the real numbers. It's got infinitely many things in it, and make it into something smaller. Now, granted, there's still infinitely many degree measures in here, but now some of my group elements are going to have finite order instead. Okay, so I am planning to have just one more lecture on tying up some loose ends for the group theory unit. And very soon we will be talking about solutions of polynomial equations. Those will get us to elliptic curves. And it is the points of the elliptic curve that are going to form a group. So there's some geometry yet to be resolved in this course. In some ways, this is going to be a bit more abstract than the groups we've been seeing, but I do hope that the ideas of working with the wallpaper groups helps to get us ready for the idea of a group that is based in geometry instead of just straight up numbers. All right, that is it for today.